Hello everyone and welcome back once again to this lecture series on aluminum based alloys and metal matrix composites. So we have been discussing about strain hardening or cold working, and we have seen that there are two kinds of strengthening mechanisms with regard to cold working. One is related to dislocations pile up at barriers leading to development of backstress, which opposes the applied stress, and that is how it leads to strain hardening. Okay? And the other one is due to dislocation cutting mechanisms, which comes up when dislocations move on the slip planes and interact with other dislocations moving on the slip plane. So, the hardening due to dislocation cutting mechanism occurs over short range, and hence the effect of cold working can be removed by thermal energy, that is heating to some elevated temperature. So, we have seen that this process of heating the material to remove the cold working effect is known as annealing. And this is what we are going to discuss today in this lecture in more detail. Okay, so annealing is nothing but a heat treatment process wherein you heat the material to certain elevated temperature and hold it for certain period of time. And this will be followed by slow cooling. This is critical because if you do not cool it slowly, then the kind of microstructure or the properties that you are expecting may not be obtained. Okay, so depending on the cooling rate, you have another process which is very similar to annealing, but it is not really annealing. That would be called as normalizing. So in order to ensure slow cooling for the annealing process, what is done is after the hold period, you start cooling in the furnace itself. This will ensure that it cools down slowly. On the other hand, if you want to increase the cooling rate, you can simply take it out from the furnace and do air cooling, either natural air cooling or it can be also forced air cooling. If you want to increase the cooling rate further, it can be done through forced air cooling also, right? If you do that, the process would be known as normalizing, and it will give you a very different kind of microstructure altogether compared to what you would get from annealing, and therefore the properties can also differ significantly when you normalize the material instead of annealing it. Okay, so you need to take care of the cooling rate while doing the annealing process. So now let us try and understand as to what exactly happens during annealing, which restores the material. So you can say this is a kind of restoration process. Restoration in the microstructure, which in turn leads to the restoration of some of the properties. Okay. So if you look at this in terms of the dislocation mechanism, it is basically how the dislocations will be eliminated or annihilated from the material. because in the cold worked state we have already seen it has very high dislocation density, dislocation tangles, cell structures and all that. And unless you remove those, the material is not going to be restored. Okay. So this restoration process by annealing is basically elimination or annihilation of dislocations. Okay, and there is a particular process or a particular mechanism through which it can occur. Okay, and that is what we are going to discuss right now and try and understand as to how exactly that happens. The process goes by the name recovery and recrystallization. Recovery is basically the early part of recrystallization. Before the recrystallization actually occurs, the material will go through the recovery process, and this is basically the annihilation and elimination of the dislocation density and restoration of some of the physical properties which would have been reduced or lost during the cold working process. Okay, so we need to look at the ways in which dislocations can be annihilated or eliminated from the material. So during recovery, some of the physical properties such as the electrical conductivity will recover. However, there is no significant effect on the mechanical properties. And the microstructure also does not change to any significant extent. So there is no observable change in the microstructure. All right. But what happens that leads to recovery of some of the properties? That is something we need to understand as to what is the mechanism of that. So after cold working or plastic deformation, there are defects like dislocations and point defects. Okay, so the increase of the density of such defects is actually affecting those properties which we are looking to restore, right? So if the density of such defects is reduced, then these properties will also get restored. So during recovery, as the material is heated, the density of point defects decreases. So this is one such mechanism through which the properties such as the electrical conductivity will recover. So when the density of point defects decreases, properties which are most sensitive to point defects such as the electrical conductivity will recover. And the annihilation of the point defects occurs when they move to the surface or grain boundaries. Okay. Then the density of dislocations will also reduce. So this will occur if the dislocations are annihilated by some mechanisms. For example, on the slip plane, if there are two dislocations having opposite signs, one having a positive sign, a positive edge dislocation like this, and if we have another edge dislocation which is negative moving on the same slip plane, then when these two come together, they will actually annihilate each other and the lattice distortion will also be eliminated, right? So this way the dislocation density can reduce. Now when you have dislocations of same sign, then this annihilation can take place by some kind of rearrangement into a low energy configuration. For example, dislocations can get rearranged into a tilt boundary. So if there are a number of dislocations, they can get arranged like this in an array and form a tilt boundary. And this way, the number of dislocations in the lattice, in the grains, will reduce. Okay. Another way by which the dislocations can get rearranged in such configurations into such low energy configuration is by what is known as polygonization. Okay, so let's say there are dislocations on the slip plane. When the material is heated, these dislocations can get rearranged into an array like this. Right? So if you have a grain like this, the dislocations will get rearranged in this kind of arrays, and in the process it will reduce the energy of the material, because in this arrangement the energy of each dislocation will reduce, and that in turn will reduce the energy of the system. So this is another way by which the dislocation density can reduce, and also leading to a reduction in the energy of the system. For example, if you consider this area now, this is free of dislocations because the dislocations now are arranged into this array, right? And as I said, in this process, the energy of the material is also reduced. So we have seen that the recovery process restores some of the properties. Properties such as the electrical conductivity or the electrical resistivity will be affected by this process. The electrical resistivity, in fact, will decrease due to the recovery process. This is because of the fact that the dislocation density is reduced, and therefore there are less number of scattering centers for the electrons, because these dislocations can also act as scattering centers for the electrons, which are the charge carriers for the electrical conduction. So when the dislocation density is reduced, there is less scattering of electrons, and as a result of that, the electrical resistivity is decreased and the conductivity will increase. So this recovery, as I said, precedes the recrystallization process. Recrystallization, as the name itself suggests, is basically nucleation of new strain-free grains. That is how you can define the recrystallization process as nucleation of new strain-free grains, because as you would have seen before, the grains after the cold working process are strained, are deformed. So if you want to recover them, you need to actually nucleate new grains which are free of strain. Okay? So that is the process known as recrystallization. And there is a particular mechanism by which the new grains can form. So let us look at those nucleation mechanisms by which the new strain-free grains can form. Right, but before that, let me also tell you one more factor or parameter that you need to keep in mind while talking about recovery is the stacking fault energy. This has a huge bearing on the recovery process, because recovery is all about arrangement of dislocations into a low energy configuration, as we talked about. So for this to occur, the dislocations have to move and join this kind of arrays for them to be annihilated, right? So for this to occur, you need the dislocations to move freely, so that they can come and join along these regions, forming this kind of arrays. Okay. So as you know, stacking fault energy is one parameter which controls the cross slip of dislocations. What is cross slip? You can probably visualize from this particular picture over here. Here, this is a diagram which depicts the cross slip. Here you have a dislocation loop. One side of the loop is edge in nature, and another side is screw. So this side, the X and Z sides that you see, that is parallel to the Burgers vector, as you could see. So that is screw in nature, and the other side, this W and Y, these two sides are edge in character, right? So if you have intersecting slip planes like this, the dislocation can move from one slip plane to the other slip plane, as long as these two planes contain a common slip direction, right? So you can see as the dislocation moves along this particular one plane, it can go to another plane like this, it can cross over to another plane having the same slip direction, and then it can go to another plane again if there is a common slip direction between the second plane and the third plane. Okay, so this process of The dislocation crossing over to another slip plane having a common slip direction is known as cross slip. And this is a process which can actually aid the dislocation movement, right? Because it can easily cross over from one slip plane to another, and as a result of that, the movement of dislocations becomes easy, right? So this would depend on the stacking fault energy of the material, because for this to happen, for this cross slip to occur, the gap or the width between the partial dislocations should be minimum, or the stacking fault width should be minimum, which also means the stacking fault energy is higher. Okay, lower the stacking fault width, higher will be the stacking fault energy. And for materials having higher stacking fault energy, dislocations can easily cross slip and move over other intersecting slip planes also, right? So having a higher stacking fault energy means it is easier to move the dislocations through the lattice of such materials, okay? And therefore, the tendency for the recovery is going to be higher, because dislocations can now move and go to these kind of regions and arrange themselves in this kind of arrays, okay? On the other hand, if the stacking fault energy is low for such materials, recovery will be less. Right, so with regard to recovery, stacking fault energy is a very important parameter. Now comes the next stage. As you continue the annealing process, you may have the nucleation of new strain-free grains, or the initiation of the recrystallization process. We have already defined what recrystallization is, and there are certain rules or laws which govern the recrystallization process. The first one says that you need a minimum amount of plastic deformation to initiate recrystallization. If the degree of deformation is below this critical level, then no matter at what temperature you heat the material, recrystallization is not going to happen. Okay. And higher the degree of deformation, lower will be the temperature needed for recrystallization, and vice versa. Annealing time is also a factor. Increasing the annealing time decreases the recrystallization temperature. You can say that doubling the annealing time is equivalent to increasing the recrystallization temperature by 10 degrees Celsius. Okay, so that's the time temperature relationship for this particular phenomena. And vice versa. That means if you increase the temperature by 10 degrees Celsius, your time will be half, right? So here we are talking about formation of new grains which are strain-free. So the grain size after the process, after the recrystallization process, that means the recrystallized grain size, if you talk about, that depends on the degree of deformation. The greater the degree of deformation and the lower the annealing temperature, the smaller the recrystallized grain size. The fifth rule says the larger the original grain size, the greater the amount of cold work required to produce an equivalent recrystallization temperature. So it also depends on the initial grain size. Right? The larger the original grain size, the greater the amount of cold work needed to produce an equivalent recrystallization temperature. The recrystallization temperature decreases with increasing purity of the metal. And the amount of cold work is also dependent on the working temperature and it increases with increasing working temperature. So in proper term, you can say that the amount of deformation required to produce equivalent recrystallization increases with increasing working temperature, right? So these are some of the rules that govern the recrystallization process.
And with this, we can conclude this lecture, and the rest of the things that we have on this particular topic will be taken up in the upcoming lectures. Thank you for your attention.